Hello, everyone. Thank you for coming. It's a great pleasure to be here today speaking to all of you. You heard some wonderful things from Dr. Bawa and Sandesh about the Eastern Himalayas, the effect of climate change on biodiversity and the entire region. I'm going to take you to some very different places. Over the last 5 to 6 years, I traveled to some very remote places on Earth, mainly to look at telescopes and physics experiments that are being used to answer some very, very big questions in physics. And one of the things that struck me as I was doing these travels is that you might think that physics, as it is practiced, and climate change have probably nothing to do with each other. It turns out that if we continue with what we're doing to the Earth, even physics at its extreme is going to become impossible. And I would like to talk to you a little bit about that, how sustainable living, how worrying about climate change is all going to even impact the science that we do in some of these extremely beautiful and extremely silent places. And it's the silence of these places that I want you to focus on, because it's that silence that makes the physics possible. So, but before I take you to the places where modern physics is being done, just a brief look at a historical place. This is the Mount Wilson Observatory near Pasadena, California, and it's the home to what must be one of the most famous telescopes in the history of astronomy. The dome that you see on the left is the dome that houses the 100-inch telescope, and this is the summit of Mount Wilson, which is right outside Los Angeles, and it's a mile-high mountain. And in the winter of 1903-1904, none of this was there. An astronomer called George Hale, he came all the way from Wisconsin looking for a particular place to build the next big observatory. And at that time, just to give you an idea of what our conception of the universe was, when we looked up at the night sky, we thought that the entire universe was just the Milky Way. And this included people like Einstein. Everyone involved at that time thought that our universe just was the Milky Way and there was nothing outside, except that people could see with their telescopes of the day some faint clouds in the sky. These clouds were called nebulae. Nebula is Latin for cloud. But the telescopes were not good enough to tell us whether these nebulae were within the Milky Way or outside. And it was in that context that George Hale was looking for a place to build the next big telescope so that they could figure out this problem. And he comes to this mountaintop in the winter of 1903. There was an old shack at the very top of the mountain. He lay down and the whole shack was broken down, and through the roof he could see the night sky. And looking at the night sky, absolute darkness, he realized that he had found the perfect place for the next telescope, and he started building what's now called the Mount Wilson Observatory. And this observatory, I'll tell you exactly what was done there, but just to give you these are some of the buildings there at the very top. And just to mention this particular building, it's called the Monastery. George Hale, when he built the observatory, he felt that he wanted his astronomers to have a place of repose, of quiet, to do their work. He had been extremely influenced by monks and their monasteries in the Mediterranean, so he thought he would have a similar place for astronomers up here. And so when he built his his observatory, this was the 100-inch telescope. So this is inside the dome. You can't quite see much because it was very dark inside the dome. But this was the instrument that an astronomer called Edwin Hubble began using in order to figure out something very profound about our universe. And Hubble started using this telescope to figure out how far away these nebulae were. And he was the first to understand that the so-called Andromeda Nebula, which today we call the Andromeda Galaxy, it's our nearest giant galactic neighbor, is actually about 1 million light years away from us. That was his measurement. It turns out that it's actually 2.5 million light years away from us. But nonetheless, in the early 1900s, that was an incredible achievement. He figured out that these clouds that we were seeing in the sky were actually other galaxies that were further away. And more importantly, what he figured out was that these galaxies, not only were they outside the Milky Way, but they were all moving away from us. So the further the galaxy, the faster it was moving away. So in a sense, he figured out a mathematical relationship between how far away a galaxy was and how fast it was moving away from us. And if you worked backwards in time, what it told you was that all of these galaxies, at some point in time, all of the matter in the universe that you could see through your telescopes, all of that must have been at one point, sometime way in the past. So that was our beginning, that was the beginning of our understanding that the universe must have begun with a Big Bang. So the Big Bang theory essentially began with observational cosmology at this particular observatory, and this is the telescope that began it all. And when, the reason I bring up Mount Wilson is that Mount Wilson today cannot do any of this astronomy because of the light pollution from the greater Los Angeles area. So the entire region, which at one point 100 years ago was silent, silence in this particular case is about silence from light pollution, which is very, very important for optical telescopes. And today you can't do that in that area because of Los Angeles and the surrounding areas. There is so much light that none of these kind of observations can be done from there. I wanted to get a taste of sort of what Mount Wilson might have been 100 years ago. So I traveled a little further up north along the coast of California and actually came to a monastery that exists, a real monastery, a Christian monastery where silence is the way of life. So I stayed there for 5 days, and these are just some of the pictures from that monastery. And one little story I want to tell you is, this is Father Robert. In the monastery, you could not talk to anyone except at the reception. So you would go to the reception and you would interact with the monks. And I was telling Father Robert that I had been traveling around the world looking at telescopes, and I was visiting his monastery in order to sort of write about this metaphorical link that I saw between what the monks were doing with their silence and also what astronomers were doing on mountaintops. And he started smiling. He said, my name is Father Robert Hale, and the observatory that you've just come from, Mount Wilson, was built by George Hale, and George Hale and I come from the same Thomas Hale who left England in 1600 and came to the US. So here I was trying to find a metaphorical link, and this monk and the astronomer who built the observatory that I had just visited were actually related. So this was an amazing place to get a sense for what Mount Wilson might have been 100 years ago. Just a shot of the Pacific, sunset over the Pacific from the monastery, and you can get a sense for what silence means in some of these places. Now going forward to what is happening today in physics and why silence and of these various regions means a lot, I just want to briefly tell you about the state of our understanding of the universe. It might come as a shock to most of you that all the physics that we have to explain the universe explains only about 4% of the universe. So the matter that we are made of, everything that you see in this room, all the stars, the galaxies, everything that's made of electrons, protons, neutrons, the things that we understand, makes up only 4% of the universe. Only 4%. Astronomers think that 23% of the universe is made of something called dark matter. I'll come to that in a bit. And 73% of the universe is made of something called dark energy. So dark matter and dark energy, the reason they're being called dark is because we don't understand much about those things. So let's take dark matter first and figure out sort of what on earth that might be and how do we even go about understanding it. And for that we need to go into a deep mine in a mine in Northern America called the Sudan mine. It's an abandoned iron mine which began functioning in the 1880s and was abandoned in 1960s. And over the last 2 decades, physicists have taken over this mine in order to find a place, again, for a very particular kind of silence. So, and to briefly tell you about what dark matter is or might be. This is the Andromeda galaxy. This is our nearest galactic neighbor. It's 2.5 million light years away. To give you a sense of proportion, the Milky Way, our galaxy, is about 100,000 light years across. So this is really far away relative to the size of the Milky Way, but relative to the size of the universe, this is like being next door. And in the 1960s, an astronomer called Vera Rubin, she was measuring how the stars are going around the galactic center, how fast they're moving across the center. And so essentially she was trying to see stars near the center, and she was trying to measure the speeds of the stars as you moved away from the center all the way to the edge of the galaxy. So you would start measuring the stars here and go all the way down to the edge of the galaxy. And what she expected to find, and in fact what most astronomers expected, is that the velocity of the stars near the very center should be much, much higher than the velocity of the stars as you move towards the edge of the galaxy. And this is something you can understand better if you think of the solar system. The planets that are closer to the sun are moving much faster than the planets that are further away from the sun. So Mercury is moving the fastest, and as you move away from Mercury, Venus, Earth, Mars, and so on, the planets start moving slower and slower. And this is simple Kepler's laws, Newtonian mechanics, and that's exactly what was expected of the stars in the galaxy. But what happened was that when Rubin started measuring the velocities, she found that there was absolutely no change in the velocity of the stars as you went out towards the edge of the galaxy. What that meant was that the gravity of the galaxy that was holding together all the stars had to be much, much greater than can be explained by just looking at the galaxy. By just looking at the stars, the dust, the gas, the visible light, you can estimate the mass of the galaxy, and that mass is nowhere near enough to keep the stars in place. So essentially the amount of matter that must be there in order for the stars to be moving as fast as they are is about 10 times greater than what can be estimated from the visible matter. So, and that has come to be called dark matter. And we think it's out there because we can see the influence of dark matter on the way the stars are moving. And you can examine the universe at all scales, not just at the scale of a single galaxy, and you find this relationship that there must be a lot more matter out there than we can see. And that so-called dark matter does not interact with normal matter. In fact, theories have shown that if you were to pile up dark matter, or rather if you were to pile up lead from here to the sun, that is 93 million miles of lead. Now lead is a very, very dense material. And if you were to fire a dark matter particle at that stack of lead, 93 million miles of lead, the dark matter particle has a 50-50 chance of going right through. So which basically what it means is that dark matter particle does not interact with normal matter. It exerts a gravitational influence, and the only way you can possibly detect a dark matter particle is if it were to hit the nucleus of an atom straight on. But the nucleus is such a small part of any atom by volume that the chance of a dark matter particle hitting the nucleus is extremely, extremely small. But the numbers are in our favor. Remember I told you there's 10 times more dark matter in any galaxy than normal matter. So dark matter should be all around us. If the theories are right, it should be all around us. If you stick out your hand, about 1 billion dark matter particles should be crossing your hand every second, right? So, but it won't interact with it, just that's the nature of the particle. How do you find, how do you detect such a particle which doesn't interact with anything? And the basic idea here is to build a detector that can look for the collision of this dark matter particle with the nucleus of an atom. So you take something like a very, very pure crystal of germanium and wait for the collision of a dark matter particle with the nucleus of a germanium atom. That collision will set the crystal vibrating, and you should be able to pick up the vibrations. But this is really hard to do because crystals at room temperature are already vibrating, so you will never be able to pick out this faint signal. It's like, imagine a very choppy lake with a lot of waves, and if you chuck a stone at it, there is no way you can pick up the ripples caused by the stone because of the waves on the surface. But now imagine an absolutely still lake, and if you chuck the stone at it, you would be able to see the ripples of that stone. So what the scientists are trying to do is something quite analogous. They have cooled down a crystal of germanium down to absolute zero or near absolute zero. You can't get down to absolute zero, but, that's about minus 273 degrees centigrade. That's an extremely cold temperature. What it does is it completely stills the germanium crystal, and now if a dark matter particle were to hit that germanium crystal, you can pick up the vibrations and maybe understand something about the dark matter particle itself. And unfortunately, if you try to do that experiment on the surface of the Earth, there is so much noise that you will not be aware of. There is a lot of ambient radioactivity that will create the same signal. If you went and stood near such a crystal, there is enough radioactivity in your own body to cause a signal in the detector. Cosmic rays are constantly streaming down at us from outer space, and those cosmic rays can cause the same signal. So essentially, the astronomers are looking for an extremely quiet place that would be quiet enough for them to see this signal away from the noise on the surface, and that's where a mine comes in. A mine, so this particular mine, I'm about to get into a mine which is about half a mile underground in Minnesota in North America. And this is the cage that is going to take us down into the mine, and just have a look at the dimensions of the cage. This is the only way to go down into the mine. It's about 4 feet by 4 feet by 10 feet, and that's the absolute, that's absolutely the only way you can get into the mine. So just keep that in mind as we go forward. The shaft is half a mile long. It takes about 3 minutes in complete darkness to descend into the mine, and when you go all the way down and the doors open, you see this little sign which tells you basically that you're half a mile underground. And if you were to turn left, you would see this tunnel. This is about 3/4 of a mile long, a tunnel that goes deep into the mountain that the miners had dug in over the last 100 years to get the ore out of the mountain. And if you were to go further into the mountain, you would see these massive caverns that have been left behind where the ore has been taken out. And our guide essentially shut down all the lights and lit a candle to show us how the kind of light that the miners would have used in the late 1800s to do their mining. I mean, this was the kind of light that they were working with in the late 1800s. The mine itself was shut down in 1960. Now this is what you would see if you got down the mine shaft and turned left and went all the way 3/4 of a mile into the mountain. If you were to turn right today, you would see this, right? This is half a mile underground. This is the Sudan National Physics Laboratory. And basically, there's about tens of thousands of tons of equipment out there, and all of it, every little piece of it has come down that cage. Over 20 years, bit by bit, every little piece of equipment, that could be 10,000 tons worth of equipment, has all come down that cage and been assembled underground. Even the excavator that was needed to dig this cavern, which is about 40 feet by 40 feet by 270 feet long, had to be brought down, was brought down in pieces. The excavator was assembled underground, and then the excavation started. And the reason why the physicists are down here is because the half a mile of rock above you is kind of a filter against all the noise that is there at the surface. So they are essentially deep down looking for a kind of silence in order for the dark matter experiments to work. And you can see that this is a shot of the two physicists who are taking me into the room where the dark matter detector was. And you can see that we are dressed up as if we are going into a clean room. And in fact, we were going into a clean room. You have to dress up so that there is absolutely no dust that you can carry into the near the detector. Every little piece of dust that's there around in the mine is radioactive, and that can trigger the detector. I had cameras and tape recorders with me, and all of it had to be wiped clean with alcohol, because the tape recorder, for instance, might have had a thumbprint, my fingerprint, and fingerprints have moisture, and human moisture is radioactive enough for the detector to be triggered. So it's that kind of care that they're taking in order to build a detector that is completely shielded from the noise of the outside world in order to see what they're trying to see. Just another anecdote about the detector. To keep out radioactivity, they use lead. You know that lead is a good way to keep out radioactivity, but lead itself, there are isotopes of lead in the new lead, sort of lead-210, which is itself radioactive. So the radioactive isotope of lead, which is normally found in freshly mined lead, will itself be radioactive. So in order to, how do you shield your experiment from radioactivity using lead if the lead itself has some element of radioactivity? And for that, what these guys did was they went salvaging for lead in ships that have sunk off the coast of Europe 200 to 2,000 years ago. These ships have lead in which the radioactive isotopes have decayed. So they've been using those, that lead to further shield the experiment from the new lead. So they'd go to extraordinary lengths in order to create an experiment that is extremely silent. And unfortunately, so far, none of these experiments, there are probably 10 to 20 experiments happening in mines all around the world, that none of them have yet been able to find this so-called dark matter particle. Let me just move on. And so what these experiments, the one that I showed you, what they're trying to do is trying to detect dark matter directly. They're essentially trying to look for the direct interaction of a dark matter particle with your own experiment. But there are indirect ways to find out about dark matter. Again, theory tells us that these dark matter particles will be accumulated at the center of our galaxy where there is a supermassive black hole. At the center, there will be enormous amounts of dark matter particles, and these dark matter particles should be colliding with each other and generating other particles that we know about, particles called neutrinos, for instance. And you can build telescopes that are looking at the center of the galaxy, trying to look for these neutrinos. And one of the places in which, one of the places where such a telescope exists is Lake Baikal in Siberia. So I had to go to Lake Baikal in the winter, and you'll see why. This is an extraordinary lake. It is extremely pure water, which is why the telescope is out there. It's actually an underwater telescope. And the purity of the lake is very crucial to the experiment. This lake is about 650 kilometers long. It's about 80 kilometers wide at its widest, about 40 kilometers wide on average. It is about 1.7 kilometers deep on average. It has 80% of Russia's fresh water. It has 20% of the world's unfrozen fresh water. So that's how massive this lake is. And I was there in winter to go see the physicists who are working with this particular telescope. So this telescope is an underwater telescope that is trying to look for neutrinos coming from the center of the galaxy. Neutrinos are subatomic particles which, when they hit water, they generate a blue light, and it's this blue light that they're trying to look for. So within hours of reaching Lake Baikal, I realized that we actually had to travel on the ice to get to the experiment site. The lake was completely frozen, a meter thick ice, but it had lots of cracks. It was a very frightening journey across the lake. But within 2 hours of getting there, I got my first taste of Russian science, which is a stopover for vodka at 10 in the morning. So this was our first stop. And you can see that this was the scenery that greeted you in winter on Lake Baikal. So the lake is entirely frozen and vehicles are moving around on top of the ice. And this was a scene from where we were stationed near the shore. And this particular section of Lake Baikal is about 40 kilometers wide. So those mountains are 40 kilometers away, so you can imagine how big they are. And those line of black dots that you see there, that's where the scientists were working. And when I went there, this is what I saw. People working on the ice, trying to maintain the telescope. And I'll tell you in a little bit what the telescope is. But even now, when I look at this picture, this is a sub-zero temperature place. We are standing on ice in Siberia, and this guy is working so hard that he had to take his shirt off because he was warm in that cold, cold place. And what they're trying to do is build these, what can be called artificial ice. These are things called photomultiplier tubes, 228 of these that are submerged deep inside the lake. And these photomultiplier tubes are looking for that flash of blue light when a neutrino hits a water molecule. And basically, what they have to do is put these detectors about 1 kilometer below the surface where it is so dark that the sunlight cannot blot out this particular signal that they're looking for. So, and I wanted to point out to you that this experiment, again, it has seen neutrinos from outer space, from the sun, from the atmosphere, but they still haven't seen the kind of neutrinos that they're looking for, which needs to come from the center of the galaxy. But to bring it back to the notion of silence, there is a reason why this experiment is being done at Lake Baikal. The lake itself is the reason why this experiment can be done there. It is extremely pure. In most lakes, you would not be able to see this blue light. So this particular lake is so clear, you can drink the water right off. Every morning we would just dig a hole in the ice and drink the water from the lake. And preserving this lake, in some sense, is crucial, not of course for the entire ecosystem and the biology and the natural aspects of it, but in a very strange way, it's a very crucial lake for certain kinds of physics experiments that would be damaged if the lake starts getting polluted. As it's beginning to be, there are oil pipelines being built on the northern shore of Lake Baikal. There are paper mills that are dumping raw effluents into the lake, and that's beginning to damage the lake. So it has an impact, and the physicists are worried. And I just want you to keep in mind that the ramifications of pollution and climate change are actually far-reaching in ways that you may not even consider. This is just a shot of Lake Baikal early in the morning. I was there sleeping in one of those cabins. A very beautiful place. Again, this is an extreme experiment that has been going on for 20 years. They have to work in winter because they don't have the money. The Russian scientists don't have the money to work in spring and summer when the lake won't be frozen. Then you would need ships and submersibles, and they don't have all of that. So they actually wait for the winter so that the lake is completely frozen over, and then they use the ice as a platform upon which to work, and then they essentially dig holes in the ice and lower their instruments all the way to the bottom of the lake and drag it back up every winter, repair it, put it back, and then they have to get out before the ice starts cracking and the lake thaws. So from a very cold place, I want to take you to, that was a cold, wet place, we'll go to a cold, dry place. But let me just come back to this chart. The two experiments that I just showed you are trying to figure out a little bit about dark matter, this unseen matter that's there in the universe that makes up 23%. There's something else out there in the universe called dark energy. This is a very mysterious thing that we don't understand, and I want to tell you a little bit about how astronomers and physicists are going about understanding this. So we'll go to the Atacama Desert in Chile. I was there in October 2004, and the Atacama Desert is a very special place for astronomy. It's on the leeward side of the Andes in South America, which means it doesn't get much rainfall. Most of these places haven't seen rain for decades, and that, as it happens, is extremely good for optical astronomy. There's very little water vapor or moisture in the atmosphere, and moisture is a bad thing for optical telescopes. So this dry place is extremely good. Also, the mountains are pretty high. These mountains are the one that you're seeing out there. That's about 2,600 meters high, which means that a telescope can avoid all of the dense layers of the atmosphere from sea level all the way up to 2,600 meters. It's looking further up, and it's looking through the thinner parts of the atmosphere. So the atmosphere is not a good thing for telescopes. So the higher up you are, the better it is. Also, the drier it is, the better it is. So this is a very special place. But there's also something else that is dramatic about the Atacama Desert. Along the coast of Chile, there is a very cold ocean current that flows north. It's called the Humboldt current, and that current has the effect of pulling down the clouds. So normally clouds that are at about 30,000, 40,000 feet altitude, in this region they are pulled down to about 6,000 feet. It's called an inversion layer. So what that means is most of these mountain tops are pretty much all year round there above the cloud cover. So essentially, when you're looking up from these mountain tops, you have 350 days of clear skies, right? And so again, there's a reason why the telescopes are being built here. These are extremely dark skies, an astronomical treasure, or rather a treasure for astronomy, so much so that the Chilean government has extremely strong laws to protect the region from light pollution. So if you are, for instance, if you have a mining industry close by, they have to fashion their lights so that the lights only shine downwards. No light can escape upwards that can disturb these telescopes. So they are protecting what is a natural heritage, which happens to be a kind of environmental silence from noise, from light pollution. And when you go there, if you are walking around these telescopes at night, you cannot even use a flashlight. You have to, your cars, any kind of automobiles, all lights are switched off. You're moving around in complete darkness, because remember, these telescopes are collecting 1 photon of light at a time from some galaxy that's 10 billion light years away. And if you just shone a flashlight at one of these telescopes, you would have billions and billions and billions of photons just landing on the telescopes and destroying anything that it might be observing. So again, the idea here is environmental silence. They have identified a place that is very special for optical telescopes, and they're using that to look at the universe from there. Now, what about dark energy? So this telescope, which as it happens is called the Very Large Telescope, astronomers, despite all the wonderful things they do, are pretty bad when it comes to naming telescopes. So they take something like this, these are some of the biggest telescopes in the world, and they've called it the Very Large Telescope. They're building the next one, which if you want to guess, it'd be easy to guess. They're calling it the Extremely Large Telescope, right? So, and they're not getting any better with their names. Nonetheless, these are amazing telescopes, and one of the things that these telescopes were used for in the late 1900s, or rather late 1990s, remember I told you that Hubble had sort of figured out that the universe was expanding and it had begun in a big bang and all the galaxies were moving away from us. So over the last 13.7 billion years, the universe has been expanding relentlessly, and the expectation was that over the last few billion years, maybe the expansion has started slowing down because of all the gravity of the matter and energy in the universe. The fabric of space-time must be getting pulled back, and maybe the expansion is slowing down. And when these telescopes were used to measure how the expansion was changing over the last few billion years, it turns out that our universe, instead of slowing down, is actually accelerating. The expansion of the universe, instead of slowing down, is speeding up. It's almost like space-time is blowing apart. And the only way to explain that is, at this point in physics, is to assume that space-time itself has some energy. So space-time meaning we are all embedded in space-time. This room is embedded in space-time. Our galaxies, we are all in space-time. And so this volume, apart from all of the total matter and energy in the universe, and we don't really understand what this dark energy is. So a lot of these telescopes, which are in some very remote regions, and they have to observe galaxies and the universe that are literally 10, 11 billion years, a billion light years away. So light that has been traveling for 10 billion years has to reach us. So you can imagine how sensitive these telescopes need to be, how pristine the environments must be for these telescopes to function, because any kind of noise, in this case light, ambient light from human activity, can destroy these telescopes. So there is a need for a certain kind of purity of environment for these things to function. And a lot of these telescopes now are essentially looking further and further into space, deeper into space, further back in time. And I'll take you to another place where the world's largest radio telescope is going to be built. This is something called the Square Kilometer Array, which basically means a radio telescope that is going to be made of about 3,000 antennas. And if you add the total surface area of all these antennas, it adds up to about 1 square kilometer. So there were until about April of this year, or April of last year, there were two places in the running to build this telescope. One was in South Africa in a place called the Karoo, which is just south of the Kalahari Desert, and the other one was the Western Australian outback. And the reason these two places were selected was that this will be a radio telescope, which means it's observing the universe by looking at radio waves that are coming. But if you were to build a telescope, say here, you would be able to see nothing because there is so much radio noise from our mobile phones, from our television towers, from every imaginable source of radio signals, that no radio telescope could function in an urban area, or even in a reasonably remote area in countries like India or in Europe where the population density is very high, or even in the US. But you really have to get very, very far away from sources of radio pollution. And the radio astronomy community had identified only two places in the world that could potentially be useful for these telescopes. So one was South Africa. So this is when I was driving deep into the Karoo. This is what the landscape looked like. The South Africans had identified this spot as the most pristine place that they had, where there was almost no radio pollution. And this was a sample of the dish that they had built. So there would be 3,000 of these scattered over, most of it in South Africa, but scattered all the way over 3,000 kilometers into other parts of Africa. So, and then in January last year, I also went to the other site which potentially could have hosted this telescope, which was the Western Australian outback. And you can see that the landscape is pretty similar. It's extremely remote. I mean, there are so few people there, which is also partly why there is no radio pollution there. And the Australians were, of course, building their own telescopes, and they would have had these kind of antennas. And as it happened, the decision was taken in April last year to let South Africa build the telescope. So the majority of the telescope, sort of the ones with the 3,000 dishes, is going to be built in South Africa, and there's something called a low frequency component that will be built in Australia. So they're going to split the telescope among the two countries. But the point here is that these regions have been declared radio quiet zones. There are laws now protecting these regions from sort of human radio noise. And the noise can be from anything, from satellite communications, from airplane communications to the control tower, mobile phones, television, cable. I mean, everything generates radio noise. Even high voltage lines that we string across the country to take power, there's radio frequency interference coming from those power lines that is enough to mess up these telescopes. So these are very, very protected regions. Now from these deserts to another kind of desert, but my favorite place, the highest, coldest, driest, windiest continent on average on Earth, which is Antarctica, and it's an amazing place for astronomy and cosmology. So this is the first view I got of the Southern Ocean surrounding Antarctica and the ice surrounding Antarctica as we were flying in from New Zealand into McMurdo. McMurdo is the American base in Antarctica. This is a view of McMurdo Sound. So the photo is taken from McMurdo Station, which is the American base. And what you're seeing in front is the frozen ocean. And the mountains at the very far, at the background are the Transantarctic Mountains. These mountains run across Antarctica. It's like the spine of Antarctica, separating East Antarctica from West Antarctica. And I'm going to just show you some pictures of where I was. This is a hill called Observation Hill, which is right next to the base. And I was climbing up this hill. It's a tiny little hill of 800 feet high. And you get some astonishing vistas from there. This is Mount Erebus, which is about 13,000 feet high. It's the southernmost active volcano, but Antarctica is so cold that even though this is an active volcano, there are glaciers at the very top. So you can see that the volcano is active, but you can also see that it's frozen all the way to the very top. And if you reach all the way to the top of Observation Hill, this tiny volcanic mound of rubble, you see this vast expanse of ice. This is the Ross ice shelf. So all of East Antarctica is basically a massive ice sheet, and that ice sheet is flowing down from high altitude in the form of glaciers and ice streams, and it hits the ocean, but the temperature is so low that the ice doesn't melt. It just floats on the ice, and this particular ice shelf is essentially a mass of floating ice. It's said to be the size of France. I still haven't figured out what that size should be, but that's the normal sort of comparison they keep using. It's a massive ice shelf, and I was there to actually observe a balloon launch. Antarctica is a very special place. I'm not sure we have time to go into details as to why it's so special, but I was there to observe how these long duration balloons can carry massive telescopes to the edge of Earth's atmosphere. So remember I told you that the atmosphere is not a good place for telescopes, because there's a lot of stuff that happens to light as it's coming through the atmosphere that destroys the information. So one good way of doing your astronomy is actually to go above the atmosphere, and one way of doing that is to use massive balloons. But the thing to appreciate here is that this telescope that's going to be launched is 2 tons in weight. So how do you take something that is 2 tons in weight, carry it up almost 40 kilometers, and keep it aloft for 2 or 3 weeks as it circles the South Pole, and then bring it down? So you need a very, very massive balloon for that. And so here the experiment is being connected up to the balloon. The red fabric that you see is just plastic that is covering the balloon, which is inside it. The balloon fabric, the balloon is so big that the balloon fabric itself, even though it is thinner than a sandwich sort of wrapper, the balloon fabric itself weighs 2 tons, just the fabric alone. And at the far end you can see 2 trucks there. Those are trucks carrying compressed helium. So now the balloon has to be filled up with compressed helium on the ice. So you can see the balloon being filled up. It takes about an hour for the entire balloon to be filled up, but Antarctica is so cold that the helium actually does not expand to the full volume of the balloon at sea level. It's only when the balloon is launched that when it reaches cruising altitude, which is about 40 kilometers up in the atmosphere, that the balloon fully expands, the helium fully expands, and then the volume of the balloon is 40 million cubic feet, and the balloon is 400 feet across. So it is so big that if you are standing on the ground and looking up, and on a clear day in Antarctica you can actually see the balloon, it's the size of half a full moon. It's that big, right? But at ground level it doesn't expand to that volume. Now here's the balloon being put together. So this is where the helium is getting filled, and then the balloon continues all the way till here. Here it's connected to a parachute. There are explosives here that can be detonated to bring the payload down, and the payload is connected by a parachute to this truck here, and eventually this will be launched. And I actually want to show you the launch. There's a video of a launch that there were some videographers who were there at the same time who filmed this and put together a video. And can we have some volume, please? Yeah.
Okay, release the balloon, release the balloon, release the balloon.
Some of you may have noticed that the experiment that flew up was different from the experiment that I was showing you earlier. There were 3 different flights when I was there, and the earlier slides were of a different balloon experiment. But essentially, there's something very special about the climatic conditions over Antarctica, that it's the only place where these balloon experiments can be done. The balloon just goes round and round the South Pole and it can be brought down, where you want it to land. You can't do this experiment anywhere else on Earth. And again, even things like the ozone hole are changing climatic conditions over Antarctica, and indirectly, it's not probably the main concern of humanity, but indirectly even these balloon experiments will get affected. So you can imagine that everything that we do to the Earth has all sorts of ramifications, and I'm just showing you one side of it. I don't think we have time to go through these slides, but I'll just quickly, this is the South Pole, so I was at the South Pole in January 2008, also looking at various experiments. Remember I told you Lake Baikal, they're looking for neutrinos by looking for the flash of a blue light when a neutrino hits a water molecule. At the South Pole, they're looking for the same thing, a flash of blue light that comes when neutrinos hit the ice. So they're actually instrumenting 1 cubic kilometer of Antarctic ice to build the world's largest neutrino telescope. This telescope is a radio telescope. It's called a 10-meter South Pole telescope. It's looking for radiation that is left over from the Big Bang, radiation that is literally 13.4 billion years old. And again, the environmental conditions, the pristine quality of the environment at the South Pole is what makes this telescope possible. And to my eyes, this was one of the most beautiful telescopes that I had seen. Even though I'd seen quite a few, there was something very, very special about this. I'll end by taking you to Ladakh. There is an up-and-coming observatory being built by the Indian Institute of Astrophysics, people from Bangalore. I was taken there by a physicist, Dr. Tushar Prabhu, in 2008. And this was a place where some of the things that I was thinking about sort of came together. Even though the telescope itself is very rudimentary at this point, it's an observatory that has great potential. And as we were driving by to the telescope, we passed, you can barely see it here, but that's the Hanle Monastery. It's a 400-year-old Buddhist monastery. And that is the telescope and observatory. Behind it are the Greater Himalayas. This is a picture taken from the summit of what the astronomers call Mount Saraswati. And this particular telescope is built, the entire region is about 15,000 feet in altitude. And again, there is the monastery. So I would like to leave you with this picture. It was while standing here that it occurred to me that the monks are here for a reason. There is a certain kind of silence in this region, and that's why they have their monasteries there. It's that silence that allows them to explore their inner being to the best of their ability. The astronomers are here for a reason too. They are also after a certain kind of silence. And if we destroy that silence, whether through unsustainable living, climate change, etc., we will end up with a situation where we destroy these places which we need in order to look outwards. And looking outwards at the universe is in some way the same as looking inward, because we are essentially trying to understand our own beginnings and trying to understand ourselves. And by ruining these pristine places, we will end up stranded on a planet with no ability to look outwards and hence inwards. So thank you very much.